Hi, my name is Hamid Jamshidfar. Today I'm trying to show you how to use the concepts of the previous video to plot the shear force and the bending moment for the beams. If you remember from the previous video, what we have done was using some formulas to develop some plots, and we said that we may have different distribution of the load. That could be a single force like this one, or a distributed force like this one, and based on that we would have different manners on the plot of shear force and bending moment. We said that if there is nothing on the W, for example here I have nothing, we have a constant value for V and a line for M. If we have a distribution which is constant distribution like this one, what we would have is a line for V and it's a parabola for M, like this one, a line and a parabola. And if we have a line for W, the distributed load, what we would have for V is a parabola function, and what we would have for M is a cubic function. In general, we can say that if W is x to the power of n, V would be x to the power of n plus 1, and M is x to the power of x plus 2. Right now I want to review one example with you and try to solve two other examples. Here what I have is a beam which has two supports and a distributed force which is like a triangle over there. As I said, the first step in all of these problems is finding the reactions. And actually what we have here is like this. We have two supports and two forces could be found based on that. For solving these things, what we would do is replacing the joints. Let's assume this is one of them is like this one, which can apply two forces, but here we have like a slot connection. This is this rod can slide in this support, and based on that what I would put here is a x, a y, and for B I just put by because it cannot provide any x direction force. And what I have on the top is something like this, a distributed load, and this is 3 kN over M, and I know the distance between these two is 3 meters. Okay, we said we need at the first we need to find these things. For finding these ones we need to replace the distributed forces with single forces, meaning that I get rid of this and I put the effect of that. What is the effect of a distributed load? Is the area under that, meaning that it's a triangle 3 times 3 over 2, which is 9 over 2, and that would be 4.5 kN. Why the unit is changed? Because we are multiplying this thing, which is kN times M, to a length, and the result would be kN. This would be simplified with this way. And this is the magnitude of that, this is the area of that, this is the magnitude of that. Right now we need to put it in the centroid of this. Centroid of a triangle is 1/3 of the length, meaning that this would be 1 and this would be 2 meter and meter. Okay, right now I can clean the distributed force and just put the value of the force over there, meaning that instead of that I just put the value of the things, the value of the force, and go ahead with that. Right now we can solve it. Sigma of x, sigma of y, and sigma m. Sigma of x is giving me ax is 0 because no other forces apply in that direction. Sigma of y is saying that ay plus by should be 4.5, and sigma m around any point I choose a equal to 0 counterclockwise positive, that would be, I have 4.5 times 2, this is 4.5 times 2. I'm taking integral around this is clockwise around this point, meaning that that should be negative, and I have by times 3 equal to 0. By around this point, if you put your finger here counterclockwise, this times the arm, which is 3, should be 0. I solved this at first, and what I would get is by is 9 over 3, meaning that it is 3, and just replace it here, and ay would be 1.5 kn. By having these two, you can see that I have this value and I have this value. I mentioned at the beginning that we need to replace this distributed force with a single force, but at the second step, which is here, you get back to the distributed load. Otherwise, you have changed the problem, meaning that you have removed this guy and you have this guy instead of that. We do this for finding the reactions only, not for solving the problem. We found reactions, we are done with this, and this goes, and we get back to the previous problem with reactions. Right now I have these two, which are obtained from this step. Be careful about this. We need to take care about the distributed force, not a single force. Single force is good for finding the reaction, otherwise we cannot find that. We found that, get back to the previous problem. Okay, then let's see what's happening here. I'm saying that this is a line and we are taking the integral of that. We know we have a jump because of this. We jump up 1.5, and then I have a line. Whatever I would have is a problem. Why it's going down? Because these are all negative things. I said that the direction of omega is determining the value under this, meaning that this is a negative area because omega is downward. Then it starts to get down to reach a point which we pass 0, and then go down to reach a point -3, and we get back because of this. The question here is that why we are doing this way, meaning that it could be, we have two options here. One of the options is this, which is shown. The other option is something like this. Why the parabola is like this? To make it clear why I'm choosing this one and why I'm rejecting this one. If we consider the formula, here is a place that the formula is helping a lot. We know V is integral of W dx, meaning that W is V prime, or dx dV over dx. It's the differentiation of V. Again, M is integral of V, and we can say V, magnitude of V, is M prime, or the derivative of M with respect to x. These are derivatives, and these are the magnitudes. Okay, let's get back here. I know I'm getting to 0. V, actually omega is showing the derivative of V. What is derivative? Derivative is the slope. Right now, I would say in this point, my omega is a larger value. Then my slope should be greater than 0. And here, my omega is 0, then my slope should be 0. If I choose this one, the slope over here is this way, and this is 0. If I choose the other one, my slope here is 0 and nothing, and another value. Then I choose these black ones because I know my omega is here 0, and somewhere in the middle is a negative value, and this slope here is 0 and this is a negative value. This is the way that we solve these things, and you continue that because you are getting more and more values for omega, and your slope is getting negative and more negative and more negative. If you make it like this, this is the way that you're going that way. This is 0, negative value, and a larger value in negative. And this is the slope, and that's why we are choosing this. We are choosing this one, not this one. This is the idea behind that. And we said that, okay, we are done with this, and we know V. Right now we are going to find M. Okay, I know from this point to this point I have a positive thing, and from this point to the end I have a negative thing, meaning that I start from 0 because it's a hinge, something like a hinge. I go up because I'm finding the area of this, and then get down. Okay, you may have two options here as well. You may ask me why you are not going this way. I would say we have the same concept. V is M prime, meaning that we have a value which is positive for V, and we have a positive value which is the slope of this guy, and we have 0 here which is the slope of this guy. V is the slope of M prime, and this is the true way to go there. We don't have 0 slope for this and a value for this, meaning that the blue one is not working. I get rid of that, and I know the slope is here 0, this is a value over here. Okay, and then get back to 0. If you find the area here, that would be the value over here, and if you find the area over here, that would be the value which is reduced the amount of moment over here. By doing this, you need to get back to 0. This is a checkpoint, as I said before. By finding the area of this, you need to get to -3, because this is 3, and this gets you back. These two are checkpoints. At the end of the day, I need to have 0 for the moment, and I need to have -3 here to get back to 0 by having this single force. This is it for this video. In the next video, I try to show you 2 examples using the same concept. Thank you.